So now that we've talked about barrier synchronizers and I've shown you countdown latches and cyclic barriers and phasers, and we've seen a bunch of different examples, let's kind of summarize the usage considerations of barrier synchronizers. As you've hopefully observed, and you'll get a chance with the next programming assignment to actually try this out, barrier synchronizers can be used for several different purposes. Countdown latches typically focus on actions. You can use a countdown latch as an on-off switch or an on-off latch for an entry barrier. For example, we saw the use case where you have the video rendering threads that all block at this latch until the main thread is finished with its initialization and it invokes countdown. So that'll let all the waiting threads begin simultaneously. You can also use countdown latches for exit barrier use cases where you have everybody kind of wait until some condition is reached where they can all move forward or one can move forward. So for example, you can use countdown latches to have one thread wait until n threads have completed an action. You can also, so an example there would be you could have the tour guide wait until all the people in the museum room have finished looking at something before you move on to the next, or till you let them go. You can also have one thread wait until some action is completed n times. So in this particular case, you could have the main thread wait until all the worker threads have finished their processing and decremented the count down to 0. Cyclic, and so countdown latch is flexible, but it has this downside that it doesn't support cyclic actions. Cyclic barriers focus on threads that want to do some task over and over again. So it allows a group of threads to wait for each other to reach a certain point before they make the decision about whether to continue on to the next phase. We use the assembly line as an example for that. We saw here where you could have an iteration of an algorithm where everybody has to finish before you consider to go on to the next phase. And that's often used for things called gang scheduling, which is pretty much the same equivalent of the assembly line that we were talking about before. Cyclic barriers typically require a fixed number of threads because you have to wait until they all reach the point where they're ready to go on to the next phase. So in that case, a party equals a thread. And that may be overly limited for certain use cases. So a fixed number of threads, not every algorithm, not every use case has a fixed number of threads. Of course, that's a common thing, but not everything works that way, so it could be limited. Phasers are a bit more flexible because they can be used to wait for a variable number of threads as opposed to a fixed number of threads. Of course, you could use it for a fixed number of threads where it's just n, but it's more interesting when you use it for a variable number of things because that use case is not well suited for cyclic barriers. Once again, you can use it for processing things in cycles or a one-shot type of use case. As I said before, it's probably overkill to use phasers for fixed numbers of threads. Cyclic barriers work much better there. More flexible, but it's also more complicated to program. If you go back and watch that video from last time, you'll kind of get a feeling for why it's more complicated because you have to keep track of registering parties, and there's a bunch of different ways of arriving and awaiting and arriving and awaiting and all this kind of good stuff. So that's basically the long and the short of it. As a good rule of thumb, and this is true for almost every synchronizer in Java or in general, always try to use the simplest mechanism that'll do the job. Because number one, it's easier, and number two, it's also more likely to be faster because there's not as much mechanism required to work on it.